Hi, welcome to the next in our series of Practical Electromagnetics for Engineers. We've been talking about the magnetic field, and we're going to start to wrap up the magnetic field by simply presenting some results for the permeability, which is the property of materials that can affect the magnetic field, boundary conditions for a magnetic field, and the energy in a magnetic field. And these are in direct analogy to the types of things we talked about for the electric field, and so we're not going to go through the derivation and explain them in all the detail, because really they're very, very similar in many cases. If you're following along in the book, in my class, you can read about this in Chapter 5.5, 5.6, and 5.8. So let's first talk about how materials affect magnetic fields. Remember, with electric fields we had some kind of charge Q. It creates this outward going vector electric field, and we put some kind of block of material in the way of this field, and we determined what that material was, or its properties, by this overall property we called epsilon, which was the permittivity, and we often express it as a relative permittivity, where we multiply that with the permittivity of free space. And you'll remember that for the electric field, we found the case that the molecules inside this material distort, and at least for dielectric materials, the electrons will go in that direction, while for most materials the nuclei stay fixed. This led essentially to a plus charge on one side, a minus charge on the other, that set up a field that opposed the electric field that was going through, which is shown by those black arrows right there, and in essence weakened the electric field for dielectric materials. For conducting materials, of course, the electric field is close to zero inside the material because the charges will rush over essentially and make the field zero to minimize their own energy. And of course, in dielectric or insulating materials, the electric field was in fact weakened, and so you can think of sort of it as shading or squelching the electric field. And the size of the permeability epsilon, essentially, because that's in the denominator, is how much the electric field inside the material is going to be reduced by. But of course, the electric flux, D, was unaffected by the materials. So that's just a quick review of the permittivity, or how materials affect the electric field. Things are actually quite different for magnetic fields. If you look at our generating expression, you'll see that there is no permeability, and remember, mu is the term we use for permeability. There is no permeability in our generating expression, the Biot-Savart law, so that the magnetic field created by a little element of current, let's call it dI here, which remember is pointing out of the screen at you, is unaffected by the material at all. However, in order to calculate the magnetic flux, B, we multiply the magnetic field by the permeability mu. So what does this do? Essentially, if we put a block of material with some permeability mu in the magnetic field, the flux that goes into this is going to be concentrated if mu is much, much greater than 1. This happens to be very hard for me to draw, so I downloaded this picture from a Navy training course on electricity. And you can see essentially, if you think of the magnetic field being put out by a magnet, so our magnetic field is sort of going like this, and we'd expect it to be the same on both sides. If we put a bar of material that has a very high permeability, and it turns out that iron, as we'll see, has a very, very high permeability in this magnetic field, it essentially acts to concentrate the magnetic field. And the field gets distorted and wants to run through the material that has the high permeability and not go through space. So in essence, materials that have high permeabilities can act as concentrators of the magnetic flux vectors. Another factor about the permeability is it's much more binary than the permittivity. And what do we mean by this? It doesn't mean it just has values of 0 and 1. If we look at the permeability of vacuum or air, we find it has a value mu naught of 4 pi times 10 to the minus 7 henries per meter, where henry is a measurement of the magnetic field. While permittivities, things like plastics and dielectrics, had values in the tens or 1s, 2, 3, 5, 12, stuff like that. Most materials, the vast majority of materials, have relative permeabilities. And remember, the overall permeability is the relative permeability mu sub r times the permeability of free space mu sub naught. Well, these materials have relative permeabilities very, very close to 1. Here's copper, here's aluminum. Slightly different than 1, but for all practical purposes, most materials have a relative permeability equal to 1, and so they essentially have the permeability of free space. Water is another example of one of these materials. But a certain class of materials we call magnetic materials, have very, very high permeabilities. Cobalt's on the low end with a permeability of 250. Pure iron is on the order of 4,000 to 5,000 relative permeability, and there are special alloys that are meant to use as magnetic shielding or magnetic concentrators that have permeabilities on the order of 100,000. So a very good first approximation is that a material is either going to have a relative permeability of 1, which means for most practical purposes it's not magnetic, or it's going to have a very, very high relative permeability, which means it is magnetic. And that's what I mean by binary. Materials are magnetic or they're not magnetic. Magnetic materials have very, very high permeabilities. Non-magnetic permeabilities are close to 1 or mu naught, the permeability of free space. While we're not going to go into the details here, it turns out that magnetic materials have inside them little crystal structures that are called magnetic domains. And it turns out that usually these things are not aligned. And you can see that in something that's not aligned, these arrows are pointing that way, these arrows are pointing that way, these arrows are pointing that way, those arrows are pointing that way. And essentially they don't add up to anything. However, to create a permanent magnet, you put in a magnetic field across something and you get these domains to essentially line up more in one way than the other, and with even a stronger magnetic field they'll all line up. What does this mean? It means that magnetic materials subjected to a magnetic field change their permeability. They become magnetized, and this leads to a nonlinear response, because in general, anytime you have a material that is affected by a field and in turn affects the field, the response of that material is nonlinear. And I got this diagram, and you can read more about magnetic domains at this Wikipedia site. Remember when we were studying electrostatics, we saw that the electric field vector changed when it went into a material that had a relative permittivity because of the boundary conditions. Turns out that we also have boundary conditions for magnetic fields, and they're essentially identical to those for electric fields. The components of magnetic fields parallel to a surface, either on this side or this side, are going to be the same, regardless of the relative permeabilities of the two materials. However, the relative strength of the magnetic fields going perpendicular to the surface of the material, which we call H perpendicular there, are affected by the relative permittivities the same way, permeabilities the same way they were for an electric field, and so we can come up with this expression for the ratio of the relative magnetic fields on either side. And again, just like before, this results in a bending of the magnetic fields when it goes into a material that has a permeability that's different than 1. In other words, a magnetic material. Finally, magnetic fields can store energy just like electric fields can. We learned for electric fields the amount of energy storage is pretty low. That's also generally true for magnetic fields. We found that for an electric field, the overall energy stored at any point was 1/2 epsilon, the permittivity, times the electric field squared. The energy per unit volume for a magnetic field is exactly the same, but we represent it as 1/2 mu, the permeability, times the magnetic field squared. So from this, if you're given a magnetic field and the permeability of the material, you can calculate the energy per unit volume stored in that magnetic field.